It would be really, really nice if we can make something out of that. Even the smallest contribution of just any kind of measurement. Ultimately, I do want to be able to see them oxidize iron to iron 3 from 2 to 3. I would then also like to throw some other stuff at them and say, well, could you do manganese? Could you do manganese from 2 to 3? Can you do, is it just iron? And we could look around at the tables and find other elements that have similar redox couples, and see if these little organisms can do other stuff for us. Okay. So yeah, we've got titrations, got a little bit, we could do the EDTA stuff. We'll talk about that later. We'll talk a bit about gravimetric analyses. And I also want to throw in a tiny bit about gases, not in our book. Gas measurement is problematic because your equipment leaks. That's the one big problem with measuring gas volumes and pressures, is that the equipment leaks. And I think it's worth a stab, because along with activity, right, activity replaces concentration. There's a thing called fugacity, and it replaces pressure for kind of the same reasons that pressure isn't linear. Later, about later. Okay, so we will part way through a problem. Let me go and recap that problem. Okay, I have some barium iodate, and it is sparingly soluble. So this is in the solid, this is in the aqueous, and we're going to make 2 iodates, and it's sparingly soluble with a KSP that was equal to 1.57 times 10 to the -9. Okay. We have been asked to find its solubility, but there's a wrinkle. We are told that the barium iodate is not alone in solution, that the barium iodate is in with magnesium iodate, and magnesium iodate doesn't have difficulty dissolving. If we look at KSP, now I'm going to go back. My intention on Thursday was to start this from scratch and just do it the general chemistry 2 way. And then I went, no, we'll do it the way that it's done in the book, where it does everything the long way and then says, well, if you'd done this the simple way, this is what it would look like. I have 0.033 moles per liter of this, which means, because that has no problem dissolving, that means that there is 0.033 moles of this, and there is 0.066 moles per liter of that. Twice as much, all right? If I have 1 mole of this, it makes 1 mole of that, but it makes 2 moles of this. So the concentration of barium in my equilibrium solution is going to be very small. The concentration of iodate that's in the solution due to the barium iodate is going to be 2 times very small. Certainly not as big as this number, which tells me that the concentration of iodate at equilibrium is about equal to 0.066 moles per liter. So if I was doing this the easy way, that's what I would come up with, right? Using an approximation, saying the barium is 10 to the negative 9, right? So we said, think back, if this is not 100 times smaller than that, then you can't use that approximation. Well, this certainly is. This is 10 to the negative 2, and that's 10 to the negative 9, which means the iodate that's in solution because of the barium iodate is not showing up to impact this number. Okay. So the KSP for the barium iodate we look at our equilibrium expression equation, and it says a barium iodate becomes a barium 2+ and 2 iodates. So K gets to be products over reactants, which would be the barium, the iodate squared, raised to the coefficient that it is in the balanced equation, divided by the undissolved barium iodate, which of course is solid, so has no concentration, disappears. Okay, well, I know what that number is. I don't know what my barium concentration at equilibrium is, but I do know that that number right there is 0.006 moles per liter. I'm going to square it. So I have 2 sets of numbers in this equation already, which tells me that Ba2+ gets to be 1.57 times 10 to the negative 9 divided by 0.066 squared. That comes out to be in moles per liter. I don't know what that, well, I do know what that number is, but you go find that number. Yeah. Okay, so this is the amount of barium ions in solution This is our solubility. But you know, if you talk solubility to people, they're going to immediately start thinking about grams per milliliter. If we talk about concentration, you talk about moles per liter. This is the solubility of the barium, but expressed in moles. So this is a foot in each of those worlds. This is our molar solubility. Typically, if people asked you to tell me what the solubility of barium was in a liter, we would normally be expecting that answer in grams. Solubility is usually in grams per milliliter, grams per liter, even kilograms per liter. But it's a mass per volume. This is reading like a concentration, but we're telling you that that's how much gets to be soluble. Okay? All right. That's the traditional way. So this would have been my step one. This is ignoring the effect of ionic strength. If I ignore the chapter on ionic strength, or I am ignorant of the chapter on ionic strength, that's a general chemistry 2 answer. Okay? Let's look at a 3000 level answer. Good. What you're going to have to come back to is this number. I'll write that down. I'll leave it up. 3.6 times 10 to the negative 7. Okay. Okay, if we think about ionic strength, so 2 gets to be if I go ahead and count ionic strength, and we already started this, we did part of this Thursday, that KSP, all right, I had written KSP is barium 2 iodate squared. All right, well, now that I know what I know, I have to tell the reader that that's the concentration solubility product. But I know that the real KSP is the activity of the barium times the activity of the iodate squared. The activity replaces concentration. And I also know that activity of anything is equal to the concentration of that thing times its activity coefficients. So the activity coefficients, the factor that changes our numbers here. So KSP gets to be barium 2 plus the activity coefficient of barium 2 plus, not plus, all multiplied, times concentration of iodate squared activity coefficient. All right, and we had that question that kind of went off camera on Thursday of, are we sure that we square both of these terms? And the answer was yeah. That if the activity is this times that, then when I square the concentration, I square both. So if I square activity, and activity is concentration times activity coefficient times gamma, then they're both inside the same parentheses. All right, here's where it gets useful. That versus this in terms of concentration. In terms of activity. That if I just pull these activity coefficients out, oh, you see that? Yeah, that's an iodine. These are both iodine. Okay. Equals BA2 plus, so I can frame what the difference between KSP and KSP prime is. Okay. In order to get there, we had to find the ionic strength. Let's recap that. That mu was half of the concentration of a cation times the charge of the cation. Is that it? Concentration times charge. Okay. Plus the concentration of the iodine, charge, iodine. Sure. Okay. Nothing missing from that term? It's half of the entire thing, yeah. So this half. So, you know, I don't know that there's any preference for saying just put the whole thing over 2 instead of having the half be out front. I don't know what they're thinking about. But yeah, let's keep it the way that the book says. It's not just our book. But are we happy with that? You sure? Yeah, those terms are both squared. The Z term is the charge, and it gets squared. Don't believe it just because it's on the board. Okay, so that was half times whatever the concentration of the barium was. 2 plus squared plus whatever the concentration of the iodate is times -1 squared. Oh, dang it. Dang it. All right, I'm going to ask you the same question again. Hank, are we happy with this line? This is the ionic, excuse me. Excuse me. I'm going to have to run out and get a cough drop. Finding the ionic strength of the solution not that analyte. Oh boy, that's not a barium. That's the magnesium. This is the ionic strength of the ionic solution. This one. This is the ionic strength of the contaminant. Because if it was just water, then we would be counting the bariums. But it's not just water. I have put the barium iodate in an ionic salt. Cough drop in place. All right, so that's the number for the magnesium iodate, which is the contaminant. This is the thing that is putting the bulk ions into solution. So this is half of 0.033 times 4 plus 0.066 times 1, right? Okay, better. And that came out, we figured that on Thursday. That comes out to be 0.099, almost 1, almost 0.1. Okay. What do we do with that 0.1 molar? What was the whole point? What's the whole point of finding the ionic strength? Yeah. This then goes to the table where you find the value of gamma. And we had a, I may have marked the page in the book. It wasn't particularly far in. There you go. Page 166. We've got a table of activity coefficients at room temperature. And I need to look up what the activity coefficient of the things that are in equilibrium are. So I'm not going to go search for the magnesium. The magnesium has told me what the ionic strength is. Like if this is sodium chloride generating an ionic strength, I then don't go look in the table to find the values of sodium and chloride. I go and look in the table for the values of gamma for the things that are having a hard time going into solution, okay? So I have to go find the values for iodate and for barium 2+. And the table told me that the gamma for barium 2+, and the gamma for iodate was, we found this on Thursday. Sure.
At 0.01. Barium. 0.1. Oh, 0.1, not 0.0.
Yeah.
Iodate is 0.775.
Yeah.
And barium is 0.38.
Yeah. Yeah. Those are the numbers that we came up with on Thursday. Okay. So the ionic strength of the contaminant. Right? We use the ionic strength of the contaminant to find the activity coefficients for the solutes. Use this for that. All right. I've got my activities. Activities can now go here. How much of this can I safely erase? Okay. The book just do a typo. The book has just written that, but I think they actually mean it the other way. The other way that we have been using it. All right, never mind. I'm going to put my 1.57 times 10 to the negative 9 here. I'm going to divide by 0.38 times 0.77 squared.
Yeah, 6.97.
Yep.
Times 10 to the negative 9.
Okay. So in terms of where we are, 10 to the negative 9, 10 to the negative 9, not desperately different. That's 1.57 and this is 7, which is 4 times bigger. This is 4 times bigger than that. Okay, let's see what effect that has if we went, well, KSP equals barium 2 plus iodate, right? And we're still going to have this. The amount of iodate that went into solution because of the barium is puny in comparison to the iodate that went into the solution because of the magnesium. So this gets to be 6.97 times 10 to the negative 9 is equal to the concentration in equilibrium of the barium times 0.066. So my barium concentration is 6.97 times 10 to the negative 9 divided by 0.66, which is equal some number. And it gets to be my molar solubility. When I take into account activity. The first number that we found was the molar solubility in terms of concentration. When we do it in terms of activity, it comes up with a different number. It's going to be 4 times as big. This number is 7, is 4 times bigger than 1.6. I want that to be 1.6 times 10 to the negative 6. So if I'm ignorant to the fact that activity exists, I predict that there are 3.6 times 10 to the negative 7 moles of barium dissolved in every liter. if I take into the account that activity does exist and that ions have different solubilities in the presence of ionic contaminants, then my value is 1.6 times 10 to the negative 6 moles per liter. Much bigger. These are both small numbers, but that's much bigger than that. How much bigger? What's my percentage error? Okay. If we ask, you got to think about the way that the question is framed. If we ask, if you didn't know that activities existed and you only calculated the barium concentration in solution using concentrations, how much different, how much wrong would your answer be than the person who calculated using activities? Okay, so you got to look and say the incorrect answer is smaller than the correct answer. So my error is a negative number. I'm smaller by it, okay? If I was larger by it, I might say my answer was off by plus 10%. If I'm smaller than it, then my answer would be I was off by minus 10%, okay? So now knowing that my answer is smaller than the correct answer, I just got to put those numbers in a way that makes sense to make the number be negative. Small number minus big number gives me a negative number. 3.6 times 10 to the negative 7 minus 1.6 times 10 to the negative 7. Oh, 1.6 times 10 to the negative 6, all divided by the bigger number, times 100. That gives me my percent error. And the percent error will have a magnitude and a direction. It will either be this percent plus or this percent minus, because we generated a number that is smaller than it should have been. Our numbers are going to be negative. Seems to me that the real answer is 4 times bigger, thereabouts, 4 times bigger than the number that's generated when we do it the wrong way. So 1 over 4, quarter is 25%. So just eyeballing this, it looks like I was 25% right, which means I was 75% wrong. Get a number? Yeah, yeah. So that's 77 goes, well, good grief, you were a long way off, right? And then you look at the numbers and you say, one of those numbers is 4 times bigger than the other number, which means it is 1/4 of what it should be. 1/4 would be a quarter. It's 1/4 of what it should be. It is off by 3/4. There's a relative error of negative 77%. It's a big one. Okay. So people who need to keep track of ions in complex environments, ions that are in the presence of other ions, just can't rely on concentration anymore. Which, you know, comes to be the factor of, well, you have two options here. You can either control your environment by filtering all those ions out, and then you say, yeah, well, I can't do that because I'm looking at a biological system. That biological system, you know, blood serum's got all of these dissolved ions in it as well. Plasma's got all of these ions dissolved in it. The biological ion bacteria is going to have all sorts of dissolved ions from the pond, from the spring. If I remove them, have I changed the habitat? Yeah, so now the new numbers, my clean numbers, aren't relevant. Okay. In those cases, you have to go with activities. But if you can control your environment, say, well, I did an experiment, but I did it in tap water, and my results are wrong. So I'm just going to rerun that experiment in distilled water. Go ahead and use concentrations, because in distilled water, you've got the thing that you're looking at. That's it. Unless, of course, you put two things in on purpose. All right. So our book gets to activity. Talks about pH, which we've kind of done. All of that we just did on the board, they do a worked calculation in the book, page 178, on what is the solubility of magnesium hydroxide, okay? I went outside of the book because I didn't want to use one of the examples from the book and then leave us with less examples if, oh, I have to do that again, okay? In fact, they have two examples. They do magnesium hydroxide, which is useful for us because it kills two birds with one stone, because it's got pH and it's got KSP. And then they follow that with calcium sulfate. Again, do it with concentration, do it with activity, look. So that's page 178 to page 180, broken down in steps. Okay. What follows in our book is more acid base, more acid base, more acid base. And then a bit about EDTA, which is a chelating agent which specifically pulls metals out, selectively pulls calcium out. We'll come back to that because I just don't want to beat it over and over and over. While we're here and we're talking about precipitates, let's talk about how some experimental stuff about what to do with precipitates. Okay. Do we think that we're just generally okay with this? To give you a couple of worked examples that, or have you do some, that would be an advantage, right? Okay. All right. What I'll do is I will take something from the book and I'll change the numbers. That way you can follow the logic and you can plug the numbers in. And that's, for me, that always made sense. of I don't understand everything, the big picture, but I can follow a worked example. And if I can see where the numbers belong, then the next time I'm asked, I can do it myself. Okay. Let's think about precipitates. Experimentally, there are times when we want to know what the amount of metal, it's usually a metal, what the amount, concentration of a metal is in solution. Sometimes it's an anion that they're looking for. And in cases like that, you would find something that doesn't match. Okay. From General Chemistry 1, we have those solubility rules. It says all sodium salts, all lithium salts, all potassium salts, all nitrates, all ammonium salts, all acetates are soluble. And then we get things that say most chlorides, most chlorides except for silver, mercury, whoops, that's a cadmium, lead. So this is dual-edged for us. If I wanted to know what the concentration of lead in my drinking water is, I could take a liter of water and precipitate the lead out of it. Because lead chloride's not soluble. I could add sufficient chloride to make the lead all precipitate. Now I have a precipitate of lead chloride, and if I filter it and dry it, then I would know its mass. And mass divided by formula mass is moles. And then moles divided by liters, and I took a liter of water to start with, gives me molarity. Okay? So I can precipitate lead out of solution. Unless, of course, what? What could possibly interfere with me precipitating lead out of solution as lead chloride by adding a high concentration of chloride ions into my sample? What could stop me finding the concentration? So if I scoop up a liter of water and then I add a whole bunch of chloride, I should be able to precipitate lead chloride. Filter. Dry. Weigh. Mass divided by formula mass equals moles. Moles per liter is molarity. I can tell you what the concentration of lead chloride is. Unless, of course, what could stop me from doing that? Okay, So if I'm given a sample and it is pure, then my test comes back as a negative, and I can tell the population of, name any town in mid-Michigan, hey, your water is safe to drink now because I found no lead. If you give me pure water, then my test is still valid. It's just a negative test. But if you give me a sample that you know has lead in it, using this technique, how might I go wrong? What if, as well as having lead in the drinking water, ... What if it also had cadmium? These are both poisonous metals. Silver's not poisonous. Mercury, lead, cadmium are poisonous. What if it also contained cadmium? Then I would make cadmium chloride and I would have measured too much precipitate, right? Okay, so I need to selectively precipitate. I need to know either it's the only ion that I'm looking at in this solution that is going to react to chloride, or I know that they're both insoluble, but they don't have exactly the same solubilities. How would I look that up? Where would I begin to look to find out if cadmium is more soluble, cadmium chloride is more soluble or less soluble than lead chloride? How would I go about that? Okay. I would go type into Google KSP, cadmium chloride, and then I would type into Google KSP, lead chloride, and I would see if those numbers are different. Let's do it now. KSP, PbCl2. I don't even have to finish typing, it's already given me an answer, because it gives me in Google suggests. Google suggests that PbCl2 has a KSP of 1.17 times 10 to the negative 5. Actually, further down the list, it says 1.6 times 10 to the negative 5. Okay. Further down the list, it says it's 1.6 times 10 to the negative 11. I'm going to hit return. Yeah, it's 1.6 times 10 to the negative 5. So KSP of lead chloride is 1.6 times 10 to the negative 5. Comment on its magnitude. Go. Big number, small number? Really small, kind of small, in between small. It could be smaller. Could it be bigger? Yeah. It is 10 to the negative 5 is not so bad. Not so bad. We're going to see some KSPs that are ridiculously small. Okay, now can I find cadmium chloride? Cadmium chloride. I may have to go and cadmium. No, I can't find the KSP of cadmium chloride, but what I can do is go one worse. And say, you know, it wasn't cadmium, it was mercury, because I can find that number. Four times 10 to the negative 15. Now there are a couple of different chlorides of mercury. There's mercury 1 chloride and mercury 2 chloride. I'm only showing you the mercury 2. Mercury 1 is Hg2Cl2. Don't ask why. Don't ask why it's not HgCl. It's Hg2Cl2. That's called calomel, and I think it's a bit more. Oh, I don't know. I have to look at that. So that's the solubility product of mercury chloride. Comment on its magnitude. It's very small. Okay, which of these two, mercury or lead, is the least soluble? The value of K expresses how far to the right. K is the concentration of products divided by the concentration of the reactants. So what does a smaller value of K mean? It means that the reactants haven't gone over to products yet. For solubility, we write that equilibrium this way. That the products of my equilibrium are just the solvated ions, right? The right-hand side of my equation is in solution. The left-hand side of my equation is precipitate. Which of these two is less soluble? Mercury or lead? KSP tells you which of these is the most soluble, which is the least soluble. Which is the least soluble? By a lot. By 10 zeros.
So 10 billion, right? A billion being 9 zeros. Mercury is 10 billion, with the B, times less soluble than lead as a chloride. As the chloride. Okay. So if I took this mixture, if I was given a mixture and I was told, find the amount of lead in this water, and I just added a whole bunch of chloride, both of these would precipitate. I would measure both of them as masses. I was oblivious, I was ignorant to the fact that there was mercury dissolved in my solution. And so now when I tell you the mass, it's the wrong mass. And then I divide it by the formula mass of the lead chloride and I tell you the wrong number of moles. That's if I just add a whole bunch of chloride. But if I add a little bit of chloride, and then a little bit of chloride, and then a little bit of chloride, this one precipitates, that one doesn't. Because this is 10 billion times less soluble. And each of those solubilities is an equilibrium. So they can go and come back. And if I put chloride into solution, the equilibrium says you've got too many products. So it goes forwards and backwards and forwards and backwards and forwards and backwards and settles more to the left. And it will do it with the lead and it will do it with the mercury. But the mercury is more insoluble than the lead. So all the concentrations oscillate, but ultimately the mercury precipitates and falls to the bottom of the flask. I can do, by titration, precipitations back to back, given mercury and lead in the same beaker. I can add chloride from solution to make the first one precipitate. Then I can filter it, and that leaves me only the second ion left in solution. Okay? The other thing that we learned from general chemistry is that most sulfates are soluble, except for barium and lead and blah, 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 blah. Okay. What were we told was mostly insoluble? Which anion was mostly insoluble? Because this is going to be our tactic. Turns out that most hydroxides are insoluble, most of them, except for lithium and potassium and sodium and ammonium. Okay, so lead hydroxide is going to be insoluble, as is cadmium, as is mercury, as is magnesium, as is calcium. They're all going to be insoluble. The question is one of them more than a couple of hundred times more insoluble than the other? Because if it is, I can make that one precipitate before the other one even starts to precipitate. Okay? We'll try and do one of those. We'll try and do a fractional precipitation, because they're kind of cool. What we will do
is a gravimetric analysis where you will take something, you will make it precipitate, you will dry it, you will find a mass. And there are experimental precautions that we have to take, because at the end of the day, you're going to give me an answer, and the answer is a mass, which means no spilling. Every time you touch the liquid, the solution, you take precautions that you do not spill, that nothing gets left behind. And I will teach you all of those in the coming weeks. Okay? All right. I'll see you Thursday.